is Max Hutt from Imperial, who's going to tell us about non-invertible symmetries of 2D nonlinear sigma models.
Thank you very much, Jerome. Okay, good morning, everybody. Thank you very much for the organisers, first of all, for the chance to speak to you all this morning. So I'm going to talk about some work that's appeared over the past year or so with fantastic collaborators, Chris Hull and Guillermo Arias de Margo, both of whom are here, and both of whom are also at Imperial. So this is a story that involves some old ingredients and some new. The old ones are knowledge of dualities, in particular T-dualities in nonlinear sigma models in 2D, and combining those with some novel ingredients about generalized symmetries. And I think there's also a nice geometric perspective to take on some of these results, so I'll try and emphasize those as we go through. Let me say a few words about generalized symmetries to put us all on a level playing field. So the modern way to think about global symmetries is, instead of thinking about some transformation of fields in an action, to think instead about topological operators. So these are operators which I can put in correlation functions, and I can move them around freely without changing the values of the correlators. And they come in all sorts of shapes and sizes. In particular, you can have both local operators and extended operators charged under these, which give rise to the so-called higher form symmetries. But you can also have operators of different dimensions with some sort of interaction, which you might call a higher group. And then the slightly more exotic ones, which are called non-invertibles or categorical symmetries, that I'll discuss more today. So it's been a reasonably fruitful program over the past 10 years or so. In particular, we've learned quite a lot about infrared phases of quantum field theories and how to use these symmetries to constrain renormalization group flows. And it also gives us a somewhat more systematic way to view the operator spectrum of QFTs. There's been a lot of work also on the sort of formal structure of these topological operators, particularly borrowing ideas from category theory in maths and tools such as the so-called symmetry topological field theory, which aren't just maths, they're also useful. In particular, they've been important in some of this work on infrared phases. So what we might normally think of as the composition of symmetries in this language of topological operators gets replaced by fusion. The meaning of which is that I take two topological operators, and being topological, I can move them around. So I bring them together and I understand them as one sort of composite topological operator. The simplest example just being a group. So in the case of a sort of ordinary symmetry, each one of my operators is labeled by a group element. I bring them together and I understand them as one operator, which is just labeled by the normal group product of the elements. But you could have something more funky going on. And in general, you have two topological operators that you bring together, and I can have a sum of terms on the right-hand side. And if there's more than one, then I would say this is a non-invertible or categorical symmetry, because there's then necessarily at least one of these operators which has no inverse. Good. So let me spoil my own punchline before I get into any details. I'm going to tell you that there's a large class of 2D nonlinear sigma models which have some non-invertible symmetries, and they're related to T-duality. Okay. Should say that's a nice fact, Max, but why should I care? Well, nonlinear sigma models are, of course, somewhat ubiquitous. They're important in the effective description of spontaneously broken phases. They're also crucial in the world sheet formulations of string theory. And they exhibit, or at least they can exhibit, strong coupling in the infrared and weak coupling in the UV. So you could see them as some sort of 2D toy model for the type of behavior that you get in 4D gauge theory. Now, why should you care about the non-invertible symmetries? Well, I'll try and convince you that they can be used to put strong non-perturbative constraints on our G-flows in these sigma models, even into strongly coupled regimes. And there are also Ward identities associated with them, which constrain correlation functions. Good. So the plan for the next few minutes is to tell you about a particular type of non-invertible symmetry, these so-called self-duality symmetries, and I'll exemplify it with the compact boson CFT. Then I'll tell you about sigma models and their symmetries. I'll give you an application to our G-flow constraints, and then I'll wrap up. Good. So this particular construction of non-invertibles. The recipe is as follows. I take my favorite QFT with a global symmetry, which is a finite abelian group G. And I'm instructed to split my spacetime in half, and gauge G in half of the space. Now, when I do that, I have to introduce gauge fields for G. And in particular, I have to prescribe some boundary conditions for them on the interface here. And I can do that in a way that makes this interface topological. So I can move this around. And now I want to restrict to a special class of theories, which have the property that this gauge theory is actually exactly the same as the one I started with. Okay? Which is very specific, but if I can get myself to this situation, then I have the same theory T on the left and the right. And instead of understanding this interface as something mapping me between one theory and another, I understand it as a topological operator existing within a single theory T. And if I have a topological operator, then I'm meant to understand that I have a global symmetry. The interesting thing about this construction is that it always constructs such a topological operator with a non-invertible fusion rule. Okay, so in particular, you have a sum of terms on the right-hand side. UG is the topological operator just associated to the group G that I started with. Okay, good. So while the construction is rather specific, they're actually somewhat common. You see them in 2D CFTs, like the compact boson and the Ising CFT, some 4D gauge theories, and there's plenty of other examples that you'll see as we go along. Good, so let me say more about the compact boson example. In particular, I have a scalar in 2D, which is periodic with this action, and it has two important properties. The first of which is a T-duality, so I know that the theory defined a radius r is exactly the same as the one defined at radius 1 over 2 pi r. This 2 pi is my bad choice of normalization. Super. And it also has a U1 symmetry, where I just shift phi. So if I want to go down the recipe that I gave you before, I'm meant to find a finite abelian group that I can gauge. So I just take some subgroup of this U1. All right. Let's see what happens when I play the game. I start with, people won't be able to see this because of this screen, I'm sorry. You start with the theory at radius r, and I gauge this ZP subgroup of this U1 shift. What's the upshot? Well, it's another compact boson at radius r on p. I'm just gauging one pth of the shift around the circle, so it effectively just reduces the radius by a factor of p. And then I'm meant to use a duality, so I use the T-duality to tell me that that theory, the gauge theory, is the same as the one at radius p over r. Now, for generic r, of course, the theory on the left and the theory on the right aren't the same. But if I restrict the value of r to be r squared is p on 2 pi, then they are. And the construction that I showed you before goes through, and there's a non-invertible symmetry. Okay. So that's how it goes for the compact boson. I'm now going to try and generalize that to a larger family of nonlinear sigma models. Given that time is short, I will do that in an example, and then I'll say some words about the general construction. So the example will be S3 with a B field. So I start with a 2D action like this. It has three scalar fields, theta, psi, and phi. I see S3 as a circle bundle over S2 as a hop bundle. And I write the metric on S3 as a base part on the S2, and then a hop fiber. And then I also have a B field with k units of flux. Okay, it's a choice of sigma model that you could study. And importantly, it also has a U1 symmetry by which I shift phi, the coordinate around the hop fiber. Okay. And given that I want to gauge some discrete subgroup of this U1, I should demand that it doesn't have a Hutt anomaly. In particular, there is a ZK subgroup of this U1 which does not. So let's gauge it, see what happens. One way to do that is to gauge the full U1, this shift. I couple the gauge field C to the full U1 by adding in some covariant derivatives to the action, this U1 gauge field. And then I'm going to restrict the gauge field to actually only be a ZK gauge field. I can do that with a Lagrange multiplier in this second pinkish term down here. So if I integrate out phi tilde, it tells me C is flat, and it also constrains its holomers to be ZK. But this now is just an action which is quadratic in C. So I can integrate out C. What do I get? I get this. So now let's interpret what we have. I still have a part on this S2 base, which looks like what I started with. I also have a part that looks like the hop fiber, but it comes at a different prefactor. And then I recover the same B field I had before. So we're in the same situation that we have with the compact boson, where generically this is different to the theory I started with, but at a particular value of the radius, which happens to be r squared is k on 2 pi, then this is exactly the model I started with. And then this construction, this self-duality and half-base gauging goes through to build me a non-invertible symmetry. Now, interestingly, the sigma model on S3 k units of flux at this particular value of the radius is exactly the same as the SU2 level k Weisser-Witten model. Okay? And in fact, there are other ways to see the fact that this is self-dual under some particular ZK gauging. There's a nice exposition in this paper. Good, so let me say a bit about the general case. I want to talk about sigma models with B fields. So I have a Weisser-Witten term. So my action, this is 2D QFT, W is a 2D closed world sheet. I have a term with a metric and a B field that I'm writing as a sort of Weisser-Witten term with H on a 3-manifold V, whose boundary is W. And I want to play the same game. In particular, I want a shift symmetry and I want a duality. Okay? So the shift symmetry is coming from an isometry of the target space. So let me consider a target which has a compact isometry without fixed points for technical reasons that I'm not going to talk about. And so it obviously preserves the metric because it's an isometry, and I demand that it preserves H. That's a good guess at the type of thing that you might want to have if you want a symmetry of that action. So if I have one of those, then I consider a shift of the scalars along the killing vector. Now, there's a slightly subtle conversation to be had about exactly when this is a U1 symmetry and when it's actually broken by the B field to be some discrete subgroup. I'm not going to get into the details, but the point is, take it on faith or ask me afterwards, that there is always a non-anomalous subgroup of whatever this symmetry is, and it's a ZP for some P, and the value of P is essentially given to you by H. So I always have some finite symmetry here that I can gauge. The other thing I need is T-duality. So in these sigma models with Wess-Zumino term, how does that look like? Well, the geometric picture is the following. If I have an isometry, a compact isometry of the target without fixed points, then I can always describe the sigma model by two bundles. One of those bundles is associated with the metric. Remember that I said S3 is an S1 bundle over S2. Okay, that's the example in S3. But generically, I can always think of the metric as some as M as some S1 bundle over a base if I have a compact isometry. And there's another bundle that you can sort of inherit from the Wess-Zumino term that I'm going to be schematic about. So these bundles both come with a curvature. They're both S1 bundles. And what does T-duality do? Well, it flips the radius, just like we saw for the compact boson, where now R is the norm of the killing vector. And that's the analog of the radius of the S1 for the compact boson. And it also interchanges the roles of these two bundles. So if you wish, some parts of the metric and some parts of the B field swap into each other. Okay? So now let's play the game again. I start with some sigma model, which has an isometry in the target space. It's described by the norm, the size of the circle that killing vector generates, and these two bundles F and F tilde. As I gauge the ZP that I told you about on the previous slide, what happens? Well, again, the radius gets divided by a factor of P, and then there's a calculation that you need to do to find how it affects the curvatures, but it acts like this. Then I use T-duality to tell me that that's the same theory as the one where I invert the radius and swap the role of the two bundles. And now I'm meant to demand that that's the same as the theory I started. Okay, and that's true precisely if this condition holds, which tells me that the radius of the S1 that the killing vector generates takes a particular value, and there's some constraint on the topology of the target. Okay, so we already saw that the compact boson and SU2 Wess-Zumino-Witten satisfy it. Other Wess-Zumino-Witten models also satisfy this constraint. Squash 3 spheres, TPQ, there are some nil manifolds. There's a long list of interesting sigma models which satisfy this constraint. Good, so that's the construction. Those are the symmetries that I'm talking about. Now let me give you one idea of what they're useful for. In particular, I'll tell you a constraint on our G-flows of sigma models, which no normal symmetry could tell you about, that this non-invertible can. So the general mantra is that symmetries are not broken by RG. Okay, that fact underpins, of course, to phenomenally matching. And so symmetries should give you some constraints on RG flows. And one would expect that that holds not just for ordinary symmetries, but for non-invertibles too. So let's test it. Let's take a sigma model with a target space that has a compact isometry. And let's look at the radius of that isometry, the norm of the killing vector. That is some coupling from the point of view of the 2D QFT, some parts of the geometry of the target space. And generically, that coupling will flow. But if I start at the particular value of that coupling, which is P on 2 pi, and I have this constraint on the topology of the targets, then I know I have this extra non-invertible symmetry, okay, associated with self-duality. In particular, at that value, R cannot flow. Why? Because if it flowed, then it would no longer be self-dual, and I would no longer be able to construct this non-invertible. Okay? So if it flowed, it would break this global symmetry, and that's not meant to happen. So I claim that the existence of this non-invertible fixes that value of R non-perturbatively along the RG. Okay? So let's see if that's true. Well, at one loop, it's not such a hard exercise. The beta function for the metric of a sigma model with Wess-Zumino term is a very famous formula. It looks like this, involves the Ricci tensor of the target space metric. And I can access the beta function for the norm of the killing vector simply by choosing some nice coordinates. I choose some where one of the coordinates is along the killing direction, okay? And then the norm of the killing vector is just a particular component of the metric in those coordinates. So all I have to do is look at the XX component of the beta function that I drew at the top. And with a bit of elbow grease, you can write that in terms of these two, of the curvatures of these two bundles. In particular, you'll see that if I satisfy these two constraints where I have a non-invertible, then this vanishes, okay, and the beta function is 0. In fact, you can do a little bit better, and you can check that the two-loop beta function also vanishes at that value. And in some cases, for example, when M is a group manifold, there is a non-perturbative check you can do. So this coupling R is fixed by the non-invertible. Let me give you a quick example, which is an adaptation of the S3 one, the S3 example I showed you before. Let's consider a squashed three-sphere. So all that's different from the metric and B field on S3 that I showed you before is this little L squared there. So when L squared is 1, it goes back to the S3 model that I showed you before. If you turn the wheel and figure out what constraint on the parameters of this thing I need to put such that it has this non-invertible, so it satisfies the constraint I showed you, you'll find that it's when R squared L squared is fixed to this value. Thank you. So one should expect that that value is RG invariant. Even though both R and L flow, in particular, this model flows to the Westerminer-Witten SU2 at level K in the IR. Okay, so L flows to 1 and R flows to, well, R squared is scaled to 1. Okay. In fact, this model had already been studied at 2 loops by Shipman and Schubring before, and just by staring at the form of the RG equations, they guessed that this constraint is fixed under RG and wondered why that would be so. The upshot is that there's a non-invertible symmetry preserving that value. So let me wrap up. So I told you about non-invertibles in 2D nonlinear sigma models, and they're related to these self-dualities under discrete gauging. In particular, they put constraints on RG flows, which are beyond what ordinary symmetries tell you. The ordinaries of the sigma model are the same at any value of R. Okay? R squared is P on 2 pi, doesn't change anything about the ordinary symmetries. So they're not the things protecting this value of coupling. It's a non-invertible. Okay? In particular, this construction generalizes when you have many isometries in the target space, and also to consider winding symmetries, like in the compact boson, you have U1 momentum and U1 winding. I gauged some subgroup of momentum. You could ask what happens if you gauge some subgroup of winding or some subgroup of both, and what happens. There's an extension of that to the sigma models as well. We also have some work in progress about trying to generalize this to supersymmetric models, and some possible connection to integrability. So there's a particular example that we found where you study a particular target space and demand that it satisfies this self-duality constraint, and you find that it satisfies it precisely when it is classically integrable. Seems like an interesting coincidence, and we wonder whether there's some connection to be learnt about that. Okay, very good. So let me stop there. Thank you.
Thanks, Max. Any questions?
I have a collection of related questions. If you're not at an RG fixed point, do you tend towards the system that has the non-invertible symmetry?
Great question. I have no idea. I mean, generically, there are sigma models which flow to some fixed point in the IR, and it does not seem true that all IR fixed points of sigma models admit this symmetry. So for the squashed S3, for example, it flows towards SU2 Westerminer-Witten, whatever values of the radius and squashing it starts at. If I start at the one where it admits the non-invertible, then it flows along a line that preserves the non-invertible. But if I start at some other point, it flows to the same fixed point and gains the non-invertible in the IR, so it's sort of emergent.
And if you do a gauged linear model rather than a non-linear sigma model, do you see the non-invertible even in the UV with the gauge theory?
Yeah, so I think everything we're doing here is in the UV, really. This is just manipulation of the Lagrangian, and I would say yes. I don't think that, yeah, I think so. Yeah.
Yeah. This could be useful for mirror symmetry.
Yeah, so we thought, yeah,
ideas.
maybe we should discuss afterwards, but yeah.
Okay,
I thought about this and I don't.
One last question. Sorry to hog the microphone. T-duality when you have fixed points is really cool. Does this work there?
Yeah, I would love to say something interesting. Unfortunately not. So the self-duality constraint is that the norm squared of the Killing vector takes some particular fixed value that's non-zero. So it could never vanish. So to be honest, at the start I said you need a isometry without fixed points. That would have been forced on me anyway by the self-duality constraint. Unfortunately not.
Thank you.
Just a variation of that. Is there any string theory realizations of this? For example, in NS5 grain background?
That's a good question. Unfortunately, I have no idea what the answer is. There are some examples known in the literature, particularly in SPOR, where you know what sort of topological defects come from which sort of branes in some string setup. I don't think the duality defects vary well. There are some papers on this, but I don't think it's extremely well.
But do you think that would be associated with, I mean, things that we know about in string theory. So these
I'm
particular values,
speculating.
oriented folds or other deep rings or...
My impression is that every little while, someone understands that a new type of brain is responsible for some sort of symmetry defect in the QFT. Whether one of the brains that we already know about is secretly responsible for this and we haven't realized, that's possible. But there are also, for example, speculations of new types of brains that should exist based on some sort of symmetry argument in QFT. So it's sort of working both ways at the moment, and I don't think that's a consensus.
So I think in this direction, like a best guess, I think, is that it's somehow related to a default in the sense that this half space gauging, since part of the ingredient is due to vertiduality, it sort of it reminds you of what you do for a default. But then there are things that you don't do for a default, like imposing this self-duality radius. Something.
I wonder if you can say also something about higher dimensional sigma models, because I remember in the early days of this non-invertible symmetry, there was the CP2 example,
Right.
which there is some kind, but then that was like the only example, and
Yeah.
people talked about it for a while, and then nobody came up with a decent
Yeah, and I
construction.
think the construction was slightly different. So the reason that this at least is simplest to do in 2D is that when I do this gauging, the Lagrange multiplier that I have to put in order to restrict this gauge field is itself a scalar. And so then when I integrate out the gauge field, I end up with an action full of scalars. If I study like a 3D sigma model, then instead of using a scalar Lagrange multiplier, I have to use a one-form Lagrange multiplier, and then what I end up with doesn't look like a sigma model. You could ask whether there's some more exotic gauging that you could do in, say, a 3D sigma model. That
Yeah,
might
you
work,
have to
and we
use
haven't studied that.
Zero form, higher form, usually in higher dimension.
Exactly. So maybe there's some other symmetry that you could gauge, but I don't know.
Yeah, hi. Yeah, thank you for the talk. Here, obviously, it was very important that you were gauging an abelian symmetry, right, and a U1 bundle. Is there any hope or that anything similar might work if you do something non-abelian, like instead of a square 3 sphere, you take a square 7 sphere with an SU2 bundle? Like,
Okay.
is there hope?
So the naive answer is that's probably not possible. For the reason that if I gauge, so in order to have some control over what's going on, and certainly for the Ganjamin theorists to be happy, this thing needs to be finite. That I'm getting finite. If I start gauging some non-abelian finite group, then what I get in the dual is actually a non-invertible symmetry itself in the bulk of the thing. I'm not talking about the duality defect that I construct. It's just true that in any QFT, if I start with a finite non-abelian symmetry and gauge it, becomes non-invertible. So it seems non-obvious that if I start with some theory that doesn't have such a non-invertible symmetry, and I do some gauging and I gain a non-invertible, that I'm never going to get back to the theory that I started with. I'm aware, and maybe we could talk privately afterwards, there are some somewhat contrived examples where you can do some finite non-abelian gauging and get back the same theory, but it's the one I have in mind is an extremely specific thing, so I'm not sure there's a generic answer, but maybe that is an example of a broader phenomenon. That would be very interesting.
Great, thank you.
You said that when we flow the idea that we can move out of the central, I guess, parameters, because then we couldn't use the construction we used to get that. But do we know, is this the only way to construct the, I mean, this is a way to get to the defect operator, but is it the only way?
Good question. So the sort of argument that I gave you goes both ways. So I argued that if I start with a theory which has a self-duality, then I can build this non-invertible by doing half-space gauging. In fact, it's also true that if I start with a theory which admits this non-invertible defect, so it has the fusion rule that I flashed before, if I have a defect with that fusion rule, then you can derive also the fact that the theory is self-dual. with respect to some discrete gauging. And so then I can construct the non-invertible by half. So it actually is guaranteed by it. You could take the more purist perspective nowadays and say, okay, consider a theory whose symmetry category is this, which contains this line, then necessarily it can be constructed by a half space gauging.
You know how these non-invertible symmetries that you constructed act on local operators or states in the model?
Good question. So let's say the compact boson for simplicity. The vertex operators that you might be interested in are labeled by momentum and winding. And in particular, the example I showed you is doing some gauging of some subgroup of momentum. And so it kills some vertex operators which have charges that aren't 0 mod p in the momentum. So you could think of it as dividing the charge of the momentum by p. And in fact, there's a nice mechanism going on in the background, which means that you also, the winding charge gets multiplied by p. But given that I'm dividing the momentum charge by p, generically, I don't end up at a genuine local operator in the gauge theory. So what happens is I start with some same momentum operator, I drag it through this defect, and it ends up attached to a topological line on the right-hand side.
Last questions?